Hi everyone, I'm Hadleigh, and today I'm excited to present our system for maintaining laser connectivity with high velocity targets. So the physical properties of laser light make it an appealing medium for numerous emerging mobile applications. For instance, we can leverage the fast modulation speeds of lasers to achieve gigabit per second point-to-point communication between drones, or streaming of high bandwidth VR content to headsets during active gameplay. We could also leverage the high energy density of laser beams for wireless power delivery. These next-generation applications are each enabled by a narrow beam of light that we have precisely aligned with a target. And while the directionality of laser light is key here, it also poses problems when we consider mobility. If any of these mobile devices move out of the beam, the laser-based tether underlying the application will be broken, rendering it inoperable. So to truly achieve these applications, we must have a way to continuously track a moving object and steer the laser to it, or maintain a laser tether. Prior work has looked into addressing this challenge, but typically in context with much different requirements. Most existing laser tracking and steering applications are longer range, such as satellite free space optical communication. The tracking and steering systems used here are often quite bulky, and the trajectories being tracked often have fixed trajectories, such as satellites in orbit. These characteristics are fundamentally incompatible with our emerging mobile-based applications, which are near range, typically on the meter level. They involve targets with arbitrary and varying trajectories, and will need much more portable tracking and steering hardware. So to address these challenges, we present Lasertag, a generic framework for maintaining laser connectivity with high-velocity targets. Here's a video of Lasertag in action. You can see a tracked object, in this case a tennis ball, and our Lasertag unit on the table, constantly steering red laser light to the target. Here's some more examples of different targets, including a drone. And we capture this at 240 frames per second to show just how well the tether is maintained, even as the drone moves at very high speeds. A VR headset during active gameplay. And as a fun example, a tennis ball. And you can see Lasertag's maintaining a very stable tether across all the targets. So let's look at some of the challenges to realizing this generic laser tethering system. The first challenge is a low tolerance for target localization error, resulting from the directional nature of laser beams. Here we can see a beam with a typical small divergence of 0.3 degrees. At a moderate distance of 4 meters, the beam spot diameter will be only 2 centimeters. Any target localization errors must be smaller than this beam spot size, or the steered laser beam will miss the target. The second challenge lies in integrating tracking and laser steering. To steer to a localized object, we must translate the localization system's 3D reference frame to a laser steering angle in 2 dimensions. This is actually non-trivial because it's difficult to know the origin points of the steering and localization devices, which lie somewhere within their packaging. And any additional optical elements may change the geometry of outgoing laser light, further complicating the task. As our last challenge, we must be able to perform tracking and steering at high rates. Inevitable tracking and steering latencies can cause periodic or constant breaks in a tether with a fast-moving target. The angular and tracking steering rate we must provide is particularly demanding given the near-range nature of our applications. So Lasertag's design addresses these challenges with 2 main components. First, we propose an optical design that jointly tackles the challenges of accurate localization and integration of localization with steering. And second, we propose a predictive steering algorithm for overcoming tracking and steering delays to facilitate tethering with high-velocity targets. So let's first take a look at Lasertag's optical design. Lasertag fuses laser steering with optical tracking, or tracking using a camera imaging the scene. This provides 2 main benefits. First, it's accurate, constrained by the image sensor resolution. And second, it can easily be co-located with the laser steering unit. However, one issue stands in the way of using camera-based tracking with laser steering. Any offset between the camera and laser steering device's reference frames can cause a depth ambiguity when determining the 2D angle for steering the laser. Here's a simple illustration of this phenomenon. We can see 2 3D points in the scene, possessing the same X and Y positions relative to the camera, but different depths, Z0 and Z1. They correspond to the same pixel in images, but they require different steering angles relative to the laser steering device. To address this challenge, Lasertag incorporates an optical design that intrinsically fuses the steering and camera reference frames together, thus avoiding the need to measure the offset and its impacts by eliminating it completely. The proposed design allows the outgoing laser light and a single image sensor to share an optical path. And as a result, there is now one-to-one mapping between pixels and laser steering angles, so that depth ambiguity is no longer an issue. The key to achieving this optical path sharing is a beam splitter, a common optical component used to split incident light at a specific ratio into two separate beams, usually either by polarization or wavelength. Lasertag incorporates a beam splitter that splits light based on both polarization and wavelength and is used to overlay the laser's outgoing optical path with an image sensor's incoming optical path. Laser light in our system is steered using a microelectromechanical, or MEMS mirror, chosen for its low cost, small size, and robustness. And all of the linearly polarized laser light is reflected by the beam splitter out into the scene. A fisheye lens expands the steering range to 180 degrees, and additional lenses ensure beam quality and the proper geometry of rays as they enter the fisheye lens. Meanwhile, incoming light rays from objects in the beam's path follow the same trajectory through the fisheye and are transmitted by the beam splitter onto a built-in image sensor. As a result, we achieve our desired one-to-one mapping between pixel and laser angle. This property is the crux of Lasertag's streamlined approach to achieving 2D laser steering in 3D space. Assuming we know the exact mapping between pixels and laser steering angles, we can determine how to steer to any object in 3D space from its 2D position in the image sensor. Lasertag establishes this mapping during an automated one-time calibration process. In this roughly 10-minute procedure, it scans throughout the steering range, recording the pixel associated with each pair of laser angles. And from the samples collected during the scanning, we fit two surfaces mapping pixel to steering angle. This mapping is then used on the fly to find the appropriate steering angles when a target's pixel position is determined. In our particular Lasertag implementation, we perform target tracking using retroreflective imaging. All targets are equipped with a retroreflective marker, and Lasertag unit floods the scene with light. Since retroreflective materials reflect light back to their source, the marker registers as a distinctly bright blob in the image, which we can segment and localize using blob detection. You'll also notice that the marker is made with a circular cutout region in the middle, which serves two purposes. First, it allows us to house a photodiode in the center for evaluating our various applications. And second, the distinctive shape allows us to distinguish the marker from potential confounding luminaries in the scene. And to the right, you can now see a video of our tracking in real time for a drone moving with accelerations up to 30 meters per second squared. We choose this retroreflective tracking method for its simplicity and efficiency, but Lasertag's optical design is completely generic and application agnostic, and any computer vision technique for object tracking can be used provided it is sufficiently fast. So this is the last aspect of our laser tracking and steering design, our optical design. We can now move on to our predictive steering method, designed to overcome inevitable tracking and steering delays. In particular, in our system, we face three sources of delays. The first is a delay in image capture inherent to using low-cost conventional cameras. For example, 28 milliseconds, assuming a moderate frame rate of 35 frames per second. Second, any image processing associated with tracking the target in the camera view will incur a delay, 8 milliseconds per frame in the case of our retroreflector tracking. And lastly, any steering device will exhibit some latencies. We see 2.1 millisecond latencies for sending SPI commands to our MEMS mirror. So let's take a closer look at our tracking and steering process to examine the implications of these delays. Here we have our target, in this example a drone, which will be moving throughout time. At a given timestamp, which here we will call T0, we begin capture of a video frame. It will take some time for this to complete, as discussed previously, and we then apply our localization technique on the video frame. At the end of these two steps, we will have captured an image of the drone and localized it to its position at T0. But during the time period, the drone will have moved. And when we then steer using its pixel position, which incurs its own delays, there will ultimately be significant offset between the drone and the steered spot. For this whole time, the tether has been broken. The faster the target's motion, the more severely this effect will be felt. Our predictive steering algorithm addresses this issue. Instead of a sequential process in which we steer only once, only after localization completes, we propose to utilize the historical trajectory of the target to forecast its position and mitigate the effect of delays. Upon localizing the target in a frame at TI, we use the historical positions to predict where it will be in the next frame. We then interpolate its positions between the current and predicted pixel position and perform several intermediate steers, each taking into account both the initial localization and prediction delays and the delay associated with each steer. It's important to note that these steers occur while the frame capture for the next frame is occurring, so the operations are parallelized. As a result, we can quadruple the steering rate and mitigate the effects of delays to enhance the tethering performance. In our evaluation, we use a double exponential filter to perform prediction, but any prediction algorithm can be used. We performed offline experiments with a neural network-based predictor, and we found that it decreased the prediction error by 52%. So with these design components, we fabricated a prototype of Lasertag using commercial off-the-shelf parts. Here you can see it in each of the design elements we've discussed previously, including a fisheye lens and LEDs for flooding the scene with light for our retroreflective imaging, a MEMS mirror and a laser diode, or LD, and a beam splitter, image sensor, and microcontroller for running our tracking and steering code. To evaluate Lasertag's performance, we place it in a room measuring roughly 5 by 5 meters, which the target freely moves in. The target object is augmented with our retroreflective marker for tracking, and we evaluate Lasertag with 3 different targets, representing our 3 emerging laser-based mobile applications mentioned previously: drone communication, laser VR, and wireless power delivery. The targets show various mobility characteristics, which I'll touch on in future slides. We quantify Lasertag's tethering efficacy in terms of 2 metrics. First, in order to evaluate the amount of laser light we deliver to each target, we place a photodiode in our marker cutout and record its voltages throughout the trial. The voltages are normalized between the photodiode's noise floor and its 99th percentile reading, giving us our normalized power metric. And intuitively, a higher normalized power corresponds to an improved tethering efficacy. Next to the Lasertag prototype, we place a dual camera setup dedicated to capturing high-speed video of both the laser spot and the target marker. And in each frame of these videos, we record the ground truth, pixel positions of the laser beam spot and marker, and use this to compute the offset between the marker and center of the beam in centimeters. A smaller offset indicates better alignment between the beam and the target and corresponds to higher tethering efficacy. So let's see how Lasertag performed. We'll start with the results aggregated across our 3 applications in terms of our 2 metrics of normalized power and offset. On the x-axis, we show the velocity of the target quantified in pixels per second. This is obtained from our dual camera setups video. And we show this because pixel velocity directly influences Lasertag's performance, since it purely perceives the world via its image sensor. For reference, the maximum pixel velocity we saw corresponds to 6.5 meters per second. We performed trials both with and without our predictive steering mechanism enabled to understand its effects on tethering efficacy. And we found that Lasertag's predictive steering mechanism delivers a median normalized power of 0.97 to targets. We performed a bridge experiment to translate this to a bit error rate and a 1 gigabit per second on-off keyed signal between Lasertag and an avalanche photodiode, and we found that this normalized power of 0.97 translates to an excellent bit rate. The median offset observed with predictive steering was 1.03 centimeters. In terms of the benefit of predictive steering, we see that without it enabled, Lasertag delivers a noticeably lower median normalized power and suffers a higher offset. The benefits of predictive steering become more pronounced at higher velocities. At the maximum velocity, predictive steering achieved a 32% higher median power and a 26% lower median offset than without. So next, let's look at the results broken down by individual application to examine the impact of some different target motion characteristics. Here we'll focus on just 2 applications for the sake of time, and we'll only discuss our normalized power metric since our offset metric shows the same trends. First, we have our drone target. The drone's motions largely were translational as it cruised throughout the room in repeated sweeps. These linear motions are amenable to prediction. Here, even as velocity increases, predictive steering maintains median normalized powers above 0.86, while without predictive steering, performance declines so that at the maximum velocity, steering without predictive steering achieves a median normalized power of 0.71. And next we have our VR results. Much of the target's motion here was angular and jittery as the person turned their head and made micro adjustments while viewing the 3D VR scene. And we see slightly different trends here than with our drone because of these motion characteristics. Predictive steering achieved a median normalized power of 0.99, and steering without prediction achieved a median power of 0.98, both with relatively constant performances across velocities. So why is this? Well, these comparable excellent performances are precisely due to the headset's motion characteristics. Although the jittery angular motions are less amenable to prediction, they correspond to what are actually small physical displacements of the marker, during which it remained within the laser beam's diameter at most times. This means that the performance gain provided by predictive steering is proportional to the translational speeds of the target. And regardless, Lasertag achieves excellent tethering performance for all applications tested. So, future work. Lasertag has opened the door to several additional explorations. First, we're currently in the process of building a portable transceiver for gigabit per second free-space laser streaming of VR content. And when we plug this into Lasertag soon, it will bring us closer to our vision of a high-throughput link for streaming VR content to mobile headsets. And also wireless power delivery. We've successfully used Lasertag to track and steer to miniature robots from a group at University of Washington, and with some upgrades to Lasertag's optical design to address the higher laser energy densities needed for power delivery, as well as some efforts on the light harvesting circuitry, we're working towards powering small mobile robots using laser light. And that's all I have. Thank you.